So in part 2 of section 6.6, we're going to move on to type 2 of the logarithmic equations. So this is what I call log equal log. So in other words, every single term will have the word logarithm or natural log on it. So again, we're going to combine each of the sides into a single logarithm. Then we're going to use this really important property. And the property says that if log base A of m is equal to log base A of n. So I've got two logarithms, one on each side, and they're equal to each other. Then the arguments have to be the same. So the bases do need to be the same also, but if you have log equal log and they're the same base, then the arguments themselves have to be equal to each other. So we're going to use this property. Don't forget, we still have to check for domain issues. So let's take a look at example 4. So example 4 says 2 log base 5 of x is equal to 3 log base 5 of 4. And again, that's 2 times log base 5 of x and 3 times log base 5 of 4. So we'll notice that every term has a log on it. We only have one term on each side. We are going to move those coefficients or the numbers out in front inside as exponents. So that's going to give you log base 5 of x squared is equal to log base 5 of 4 cubed. At this point, we have a log equal to a log. They're both the same base. So we're going to set those arguments equal. So I'm going to take x squared and set it equal to 4 cubed. I am not, repeat, not dividing out the log base 5. I can't. It's an operator. You can't divide out an operator. So what we're doing is using this property and setting the arguments equal. Well, that's x squared equal to 64. We'll square root both sides. And x is equal to plus or minus 8. Again, it's a logarithm. We have to check those domains. When I check the negative 8, plugging it in right here, it's not going to work. So the only answer that does work is a positive 8. So again, check your domains. So let's take a look at example 5. Example 5 uses a natural logarithm. So I have the natural log of x plus the natural log of x minus 4 is equal to the natural log of x plus 6. Okay, so again, every single term has a log on it. They're log bases, but it's still a log on every term. On the left side, we have two terms. Let's combine that into a single term. So that would be the natural log of x times x minus 4, which is x squared minus 4x. That's going to equal the natural log of x plus 6. And now that I have log equal to log, I'm going to come in and set the arguments equal to each other. So that would be the x squared minus 4x is going to be equal to x plus 6. It's quadratic again. So we're going to move everything to the same side. X squared minus 5x minus 6 is equal to 0 and factor. So x minus 6 and x plus 4. So x equals 6 and x equals the negative 1. Woo, okay, now we got to check them. So let's plug in the 6. When I plug in the 6, I have the natural log of 6. That exists. The natural log of 6 minus 4, well, that's the natural log of 2. That exists. And when I plug in 6 over here, I get 12, and the natural log of 12 exists. So that one works. What about the negative 1? Natural log of negative 1 does not work. You can't take the log of a negative number. So this is no good. Only the x equals 6 works as a solution. So they're very elegant problems, if you ask me. Okay, one more of this type. Example 6. A little bit longer to get on the board. We have log base A of the quantity x minus 1 minus log base A of the quantity x plus 6. That's going to be equal to log base A of the quantity x minus 2 minus log base A of the quantity x plus 3. Okay, when I look at that, I want to double check, make sure I copied it correctly. I've got an x minus 1 and x plus 6 and x minus 2 and x plus 3. And a base that I don't know what it is. It's an A. That's okay, because I do have a log on every single term. So we are going to combine each of the sides into single logarithms. This time, because there's a minus, we'll rewrite it as a quotient. So that would be log base A of the quantity x minus 1 over x plus 6. On the other side, we'll have log base A of the quantity x minus 2 over x plus 3. Okay, and at that point, because we have log equal log, we can come in and set the arguments equal. So we're going to set the x minus 1 over x plus 6 equal to x minus 2 over x plus 3. So now we're just solving an equation. In this case, what we're going to do is cross multiply to get rid of those fractions. So I'm going to multiply the left side by the x plus 3, the right side by the x plus 6. That'll give me x minus 1 times x plus 3. Again, that's this cross. Is going to be equal to the x minus 2 times x plus 6, which is the other cross. And it is. Boiling this out, it's going to give us what? X squared plus 2x minus 3 equals x squared plus 4x minus 12. The x squareds are going to cancel if I try and move them. So it is just a linear equation. 2x minus 3 equals 4x minus 12. I'm kind of low on the board. If I move the 2x to the right side, I get 2x. If I move the 12 back, I'm going to get 9. So x is equal to 9 halves. Wow, that's really low. Okay, but I have to check it. So 9 halves is around 9 halves is 4.5. That's going to help me check these. So when I plug in 4.5, 4.5 minus 1 is positive. That's all I care about. 4.5 plus 6 is positive. 4.5 minus 2 is positive. And 4.5 plus 3 is positive. So our answer of 9 halves is a good solution. And that wraps up solving the log equations. Next, we'll solve some exponential equations. Moving on to type 3, I guess we'll call it for now.